Hello, and welcome to our Analytical Foodies Bitesize Webinar series. This series will provide hints and tips to help you be successful with your multi-residue analyses. My name is Emer McCall, and I'm a Principal Market Development Manager here at Waters Corporation. The topic of this episode will look at a number of methods to compensate for matrix effects during method development. In previous episodes, we've touched on the benefits multi-residue methods can offer labs in terms of productivity. Of course, in running these methods on mass spectrometry, matrix effects are a common occurrence. In this episode, we will discuss the 4 calibration methods to compensate for matrix effects, namely matrix matching, procedural, standard addition, and internal standard corrected. It's important to remember that these approaches do not remove or eliminate matrix effects. Instead, we are simply ensuring that the matrix load, components, and thus effects are consistent across all samples. Let's begin with the approaches most commonly employed in routine analyses to compensate for matrix effects. Firstly, we have matrix matching, where we're building a calibration series from a sample type or commodity group similar to our samples under analysis. So what does matrix match calibration look like? Let's use one of the more challenging applications in pesticide analyses, anionic polar pesticides in cereals, focusing here on AMPA in wheat flour. So in this example, we've used the European Union Reference Laboratory's quick polar pesticide extraction method. While extracting all samples under analysis, we've also extracted a previously analyzed blank wheat flour sample to create our calibration series. Once this extraction was completed, we then spiked the wheat flour extracts to various concentrations to build our matrix-based calibration curve to match our samples under analysis. In the table on the bottom of the screen, we can see the spiking experiment to build our 5-point calibration curve and a blank. It's important to keep the volume of matrix to solvent consistent across all vials, as we see here in the table. Otherwise, we may begin to dilute out the matrix effects in some vials relative to others. Above the table, we see a summary of our resultant data achieved for AMPA. In this example, we have bracketed our analytical run with the calibration series. So you can see 2 calibration curves overlaid and the respective residuals plotted above. From previous method development work, we know AMPA is suppressed by matrix in these commodity types by more than 50%. However, despite this ion suppression, the matrix-matched wheat flour curve yields excellent linearity, accuracy, and repeatability. An example of the sensitivity achieved for the matrix-matched standard at 0.05 milligrams per kilogram is shown on the left of the curve. The other commonly used technique to compensate for matrix effects in multi-residue analyses is the use of isotopically labeled internal standard. In this example, we've taken the same sample set of wheat flour, but prior to injection, we've added a fixed amount of carbon-13 internal standard for AMPA to all vials. Once we've set our internal standard information in the processing method and process our data, we see a calibration curve, very similar to what we've just discussed. In the chromatography example on the screen, we can see the quantitative and qualitative transitions for AMPA, followed by the internal standard trace, eluting at a similar retention time as AMPA, but with at least 3 Dalton difference in mass to charge. Looking at the calibration series plotted on the right-hand side of the screen, the software is now incorporating the internal standard into the curve. Rather than only considering the analyte's peak area, as was done when plotting the matrix-matched curve, here the software is taking the known concentration of internal standard and its detected response into consideration. The exact information plotted on the y-axis is highlighted in grey. As we can see, similar linearity results are achieved by the bracketed and overlaid internal standard corrected calibration series. The use of isotopically labeled internal standard method's quantitative performance is further supported by the QC standards dispersed throughout the run. During data review and target links, we simply open up the statistics window, as shown here on screen. We can see good accuracy and % relative standard deviation achieved for the internal standard corrected QC standards. This is despite the presence of matrix effects, which remain at 55% in wheat flour samples. Another approach to be mentioned is procedural calibration. This method is very similar to matrix matched calibration, so samples or commodities exhibiting similar matrix interferences are grouped during analysis. However, the main difference is that we spike all matrix-based calibrants to the required final concentrations after weighing the sample and prior to extraction. This approach allows analytes which yield consistently low recoveries to be adjusted within the sample preparation procedure, while also compensating for matrix effects. So it's very useful in highly complex foodstuffs such as cereals or edible oils, especially if internal standards are not available to correct for analyte loss. Let's take a look at how the calibration series is created. Well, it's very similar to the matrix matched approach, where we plotted the peak area of each calibrant against the known concentration, which has been spiked prior to an extraction. An example of how the calibration series for solid or liquid samples can be built is summarized in the table on the bottom of the screen. As we've discussed previously, we want to keep all additions as consistent as possible, so as not to influence matrix variability between replicates. Of course, because we're spiking the weighed sample prior to extraction, we do see an increase in the amount of analytical standard, solvent and consumables used, and the time for sample preparation. However, depending on the analyte to commodity group under analysis and access to appropriate isotopically labeled internal standards, procedural calibration may be the right fit for your laboratory workflow. The benefits relative to matrix matched calibration for a highly complex sample of edible oils are obvious by comparing the trueness of the methods. And here we see just a short summary of some of the results. We've just taken some of the organochlorinated pesticides targeted in the GCMSMS method. We can see a significant improvement in the measured trueness by procedural calibration when compared against the matrix matched approach. So in using procedural calibration, we've not reduced matrix effects, nor have we improved the extraction efficiency of the extraction method. However, we can quantify our analytes more accurately without the need for isotopically labeled internal standard to correct for poor analyte recovery. One final calibration approach to compensate for matrix effects is the standard addition method. This method can employ matrix match standards, where we've spiked the calibrants post-extraction, or procedural standards, where we've spiked calibrants prior to extraction. The appropriate method, of course, depends on the analytical needs and if the analyte's recovery from sample preparation needs to be incorporated in every analytical run. For standard addition, it's the plot itself that differs from the previous approaches already discussed. We continue to build a plot of standard peak area against the known concentration. However, in both the previous methods for matrix matched and procedural calibrations, it's assumed that the blank matrix standard is in fact free or as low as possible of the incurred residues. If a blank is difficult to source or an appropriate internal standard is not available, standard addition is a good option to compensate for matrix effects and quantify the incurred residues reliably and accurately. Because the standard addition plot is using the incurred sample to build the calibration curve, this becomes our lowest calibrant. Once a linear line is created from incrementally equal additions, the curve's line is extrapolated onto the x-axis and the concentration of the incurred residue is back calculated. Building this calibration curve assumes a concentration of the incurred residue has already been estimated, and the curve built off this concentration is linear over at least 3 subsequent standard additions. Just like all the other calibration types discussed, this standard addition fit can be plotted automatically by targeting software. An example is shown for phosphonic acid in wheat flour, where an incurred residue was detected and estimated during initial analysis. Knowing the extraction method yields acceptable recovery of phosphonic acid, we aliquoted the previously extracted matrix sample rather than re-preparing the sample as procedural calibrants. Leaving one vial blank of any standard and setting this as the zero concentration standard in our sample list, Target Links automatically plots and extrapolates to yield a calculated concentration of 0.012 milligrams per kilogram of phosphonic acid in wheat flour. So standard addition is another calibration method to consider when looking to compensate for matrix effects and achieve reliable quantitation of incurred residues. So to summarize the approaches to compensate for matrix effects we've just discussed, some of the main points are outlined in the table. For many multi-residue methods, one single option may not be sufficient based on the analyte and commodity scope. Perhaps a combination of approaches may be required to either compensate for effects, as we've just discussed here, or to reduce the effects, which is discussed in another episode of this series. Finding the right solution to overcome matrix effects is often method or lab specific. Hopefully this short overview provides some guidance when selecting the appropriate method to correct for matrix effect. Thanks for viewing this episode. More episodes in the Analytical Foodies Bitesize Webinar series are available on waters.com.